Again, it's audio, essence, compression, and muxing. Al Shee is our speaker, senior staff production engineer at Skywalker Sound. Let's put our hands together. Thank you very much, Al.
Hey, thank you, everybody. Yeah, I'm here to talk about audio. I heard that we just haven't had a lot of talks about audio. So hopefully what I present today, you'll get something out of it, at least have some pointers of things to look at and explore on your own. This talk is split up into two different, kind of like two talks in one. I wanted to cover audio perception and how that is related to compression, just to give people more of a qualitative feel for, what is audio, what does the human ear do, what have biological models, how have they inspired codecs to be more efficient, especially lossy audio codecs. Won't be too quantitative there, but I'll show a couple of demos where you'll hear some sounds. And then the second part is, it's still related to audio, but it has to do with muxing audio and video. And there's nothing subjective. It's going to be more quantitative, where you'll see some calculations when you mux audio and video, and some considerations where initially it might seem like a very simple problem. It's not super complex, but there's just devil in the details for you to get right, depending on your customers' needs and their expectations. Okay, so I'm going to start a kind of a, not quite the Socratic method, but I'll throw out a couple of questions and see if, as a group, what some of the answers are. Okay, so you've probably heard of compression. Can somebody give me a one-sentence summary of what compression is, just generally?
Makes music worse.
It can, okay. Over here.
Same amount of information in less space.
Yeah, that's a great answer. Representing a raw or input data set with fewer bits, more efficient representation. That nails it. And then maybe one step up from there, how is it possible that you can take something that has a bunch of bits and represent it as something with fewer bits? How is that possible generally? Yeah. Okay, that's a good answer. Back there, and then we'll come to you. Okay, yeah, good answer. Okay, I think you're next.
Repetition, so you can encode repetition more efficiently.
Okay, so reducing redundancy, that's good. And did someone in the darker shirt have his hand up?
I was going to say redundancy.
Oh, okay. All right, cool. Yeah, we'll definitely touch on these. And then for the lossy part, you'll see other statistical biases, if you will, that we can exploit. Okay, so there's lossless compression, which is more, I kind of think of it as algorithmic. There's transforms, there's things you can do, right, to make things completely reversible, so you get back the original. And then there's lossy, and that exploits unevenness or redundancy in the human visual system, or just redundancy in the world. But it has a perceptual component. What is it that you can't detect, right? And it's usually a hybrid, right? I've never heard of a codec that only throws away information everywhere and reconstructs every piece of information only partially. It's usually you throw away info, and then what you have left, you code that losslessly, right? And then you get it back to an approximation of your original input. Okay. So yeah, so the existence of statistical bias. It can be correlation, it can be redundancy, it can be that you've got limited ranges, but a lot of the encoding has to do with, the compression efficiency has to do with probabilities that are uneven. You can have uneven probabilities in bit patterns, in regions of an image, in sound, and et cetera, right? Repetition results in predictability, unevenness, correlation, right? If you have pure white noise, you have zero correlation. Knowing something doesn't tell you anything about anything else, even the adjacent pixel or adjacent audio sample. But that's not what the real world is, right? You got strings that vibrate. They're going to have sinusoidal components, so if you know what the value is here, it's going to be only a small difference to the next sample. Okay, so I'm trying not to spend too much. I know I put a lot of detail in here, but last time I went over. So I'm going to try to move this along, but if I go too fast, slow me down. or if this is boring, we can skip ahead. Just let me know. Okay, so some other sources of physical phenomenon, I just wanted to touch on one of them, where gravity can affect how our system's visual system works or our audio system works. That also lets you create models that are biased the same way, and it's necessary biologically, right? You can't have a Swiss Army knife of a biological being running around the world wasting energy building systems that don't sense anything that's significant for survival. So gravity pulls everything down. You live in mostly a planar world. So everything is going to be biased in terms of localization within the plane. Not as much is going to be spent on, like, you know, Tiger's not going to attack you from above most of the time, right? More like, is it coming from my left or my right? I know which way to run. Yeah, like our eyes are more sensitive to oblique, like sort of slanted edges, not so much the horizontal. Vertical is kind of a close second relative to horizontal. Stereo with your ears, right? You can determine the shape of your ear provides a bit of analog signal processing, if you will, so that if a sound is directly above you, it could be equidistant from both ears, but your ear shape can modify it, and if you recognize what that sound is originally, your ear can kind of do this, what do you call it, ill-posed problem, like an undetermined system, but because you've learned, you make certain assumptions, like that's a bird, but hey, that sounds like it's from above. It sounds different from if the same bird was right in front of you. Same distance, equidistant to both ears, you can still tell that it's above you. A lot of it's to do with the ear shape. Maybe it has to do with echo off from the ground, I don't know. But localizing 0 to 360 degrees around you, you still do better at that. That's more important for survival or finding food or avoiding danger or whatever, right? Okay, so the world can affect your perceptual system, which can affect a codec, right? So like cinema screens are 16 across by 9 high, typically, right? I mean, there's different formats. There's some that are bigger than 2 to 1, depending on how the producer wanted to shoot it or director. I think it's more a producer function. But you typically don't see screens that are 16 tall by 9 across, and that's because our eyes and your head can pan many more degrees. It's more how you expect to see the real world, okay? Sorry, I'm kind of stating the obvious, but I want to set a context for some of the next few slides. Just a fun one, ChatGPT works because there's statistical bias, and it's done a very good job with billions of parameters at saying, if I'm given these words ahead, could be a question, these are the next ones, which could be the answer, right? That's one of the crux of oversimplifying there, but statistical bias has enabled us to create some pretty cool stuff. Okay, so for lossless compression, maybe some of you have studied this. This is not an exhaustive list, but this probably covers most of the lossless compression methods, at least in terms of categories. There's run length codes, right? Someone mentioned redundancy or repetition. Code books and dictionaries, you know, like here, this string's occurred 20 times. Let's put it in a dictionary, and then when we'll tell the decoder what the word is and where it appears, and boom, you know, you get a huge savings. That's why text, typically, it's easy to get 10 to 1 or higher ratios, right? Huffman codes are based on symbols occurring with 1 over a power of 2. That would be the ideal efficiency for Huffman code. Binary arithmetic codes is a step above that, where you can have arbitrary probabilities, and asymptotically, if your probabilities are stationary, you will be able to code with 100% or asymptotically approaching 100% efficiency. And those are used in video. You've probably heard of KBAC or KVLC, right? So KBAC is the context adaptive binary arithmetic coding. And what that does, that's one of the optional modes. You can pick between these two in H.264, right? And then HEVC said, let's just punt on KVLC, let's just use KBAC, right? The computation is more than 50%, at least this is true when I was working at Dolby, just to do the context adaptive probability computations. But HEVC says, we're just gonna do that. I guess compute's fast enough, and they had a mandate to be twice as efficient. Transforms do things called, there's a phrase, energy compaction. The DCT is good at shoving most of your information into the lower frequency range, Part of it's probably because you have anti-aliasing filters on sensors like CCDs and cameras. Another is that lenses are sometimes soft. So your data set itself may be devoid of some of these high frequency components, but another reason is that the eye is more sensitive to middle frequencies, not the really high frequency, especially when it's noise and there's motion. DC you're not as sensitive to as like low frequencies, spatial frequencies, or spatial temporal frequencies. And so if you can shove a lot of your information into the bands in a transform that your eye cares, the human eye cares about, you can quantize those less and then just quantize the high frequency coefficients and not care that you're introducing errors because your eye can't really see it. And that goes to what some of your answers were. Throw away stuff that's just not that important. So this is you can do transforms and still get lossless if your data set has zeros in the new domain that you've transformed to. Okay, but if you combine that, then get away from lossless, but you're kind of starting with a good transform and then using perceptual aspects of a human sensory system, then you can get some really good compression ratios and still high quality. Okay, and then lossy, we've sort of touched on. You've got biases in the human sensing system. Vision and audio is kind of what we're talking about here. And then even your sensors can be designed so that your data comes out a little bit closer to a perceptual system. For example, film, over a pretty decent range is log exposure, and your eye also is sensitive in a log sense to light. Your hearing frequency and hearing for loudness is also on a log scale. So if you were to make, say, a microphone that had log sensitivity, then the code values that come out will be proportional to what we perceive as linear changes in loudness. Okay, so either you have to process the data to be more perceptual, or the sensor itself is designed to kind of get you partway there. Okay. Yeah, and on a log scale, right? If you're on a log scale at the very high end, then every step is actually linearly very, very big. You can afford to quantize data if it's linear, but into bigger bins. Okay, so now, sorry, am I going too fast? Okay. All right, human auditory system. I like to start with diagrams of like, in the end, it's humans listening to audio, right? So might as well look at like, well, how does the ear work? So sound waves come into the ear. Again, the ear shape can help do a little bit of, again, analog signal processing. It helps you localize things beyond just having a stereo pair of ears. All right, so sound travels through the ear canal, it hits the eardrum, and then that connects through 3 bones. I forgot what the term that they teach little kids, but there's I think a stirrup at the very end. And that touches a round window, which goes into the cochlea, which is filled with fluid in at least 2 of the chambers. I think it's 2. And the cochlea is where there's this membrane, and as you go along the spiral, the membrane gets gradually more firm, and so it responds outward from the spiral to higher frequencies. And it acts as a filter bank. And it's kind of like in your eye, people have 3 and some have 4 color receptors, and they overlap in their in the light wavelength frequency domain. Here, it's audio frequency overlap of a filter bank, and your ear uses that to discern between different frequencies. Okay, so here's the basilar membrane. I think that's the one that vibrates, and there's a cross section, and those chambers are filled with fluid, and there's nerves that come out from the basilar membrane. When they vibrate, electron mobility increases in the nerves that are in that region of the membrane. Okay, so that's what you've got. It's like a microarray with frequency-tuned microphones. Okay, kind of an interesting thing. This probably wouldn't help you in your work, is my guess. But this thing called tonotopic design. Tonotopic design, it's or tonotopic. I can't even pronounce it. Anyway, it's where a certain frequency is located at a specific location. So can you see the cursor? Yeah, okay. So here, this part of your cochlea will resonate the most with a 20 hertz, like a low bass guitar note, right? And then speech will be kind of like around this area. Highest note on a piano will probably be about here. You get to 5 kilohertz. Highest note, C8 on a standard piano is around 4,200 hertz. And then once you get above there, your ear actually has a problem distinguishing between tones that are in this region. You don't have the same resolution. Right around here, your ear can hear, some people can hear within 0.2%. And just to give you an idea of scale, an octave is defined as doubling in frequency, right? A musical octave. And so on a 12-tone Western scale, a half step, which would be between, like, say, a white key and an adjacent black key, that's about 6% of the frequency. It's just 1/12. It's the 12th root, 1/12th root of, oh, sorry, it's 2 to the 1/12th power. So you get 1.059. But you can tell here, so 1/48th of a step, if I'm doing my math right. I don't know, 0.2 over 6. That would be how many steps, I guess, or percentage of a half step. Anyway, so you have fine frequency differentiation in that region, and then out here, which like babies and toddlers can hear, but probably most of the people in this room cannot, because your sensitivity decreases over time. So you have a good hearing. You can hear to 17 kilohertz if you're in your 20s, 16 if you're in 30s, and so on. And what one sort of auditory standards body says is that if you hear 8 kilohertz and above, you're okay on frequency, not necessarily discernment, but be able to detect that frequency. But if you hear less than that, you're considered hearing impaired by their definition. Okay. The cool thing here, and this is just kind of a fun fact, is the location of where things resonate, like if 1 kilohertz and 1.5 kilohertz, they'll be close to each other in the cochlea, which makes sense, right? Biologically, you would probably want something that has a gradual change all the way through rather than having it jump around. So physical construction of it probably is easier. Anyway, if there are 2 points that resonate with 2 different frequencies that are close numerically, they are close together in the cochlea in terms of the max response regions, and then the nerve preserves that spacing all the way into the brain. And in the brain, those 2 frequencies will be next to each other physically in where the neurons are inside the auditory center. So I thought that was pretty neat. And that kind of makes sense, because if you've got a filter bank and you want to determine where is something in between, like if you look at a yellow object, your red and your green cones go off. If it's orange, it's closer to your red, so your red will say, I've got more than you, green, right? I don't know if it's the ratio or difference that your brain uses to determine the color, but if you want to detect a frequency that's in between the 2, it's not like your brain says, well, I don't know, this is either 1 kilohertz or it's 1.5. There's probably some gradual weighting based on the filter outputs, and then to have them physically close means you probably could have difference neurons or however it's weighted. Okay, so I just thought that was pretty cool. Okay, let's see if there's anything here I should cover. Oh yeah, I mentioned the ill-posed problem. It's just like when you look at the real world, how can you tell, like that pizza pan's behind this one? Well, I have only a 2D projection, and so I have assumptions in my brain that I've learned, I don't know, since I was a baby or something, that says if these things, to me in my mind, I think they're the same size pans, but visually they get smaller, that means that thing's further away than that one. And same thing, if you hear dishes clang and 3 people having conversations near you, but you're talking to your friend, somehow you can still pick out your friend's words, even though the frequencies may be very similar to the conversations going on around you, right? So your brain has to be able to split, they call it source separation. It has to do it pretty reliably for you to be able to have conversations in all sorts of environments. Human communication is an evolutionary, it's a favored thing. If you can communicate well, you can work as a group. And so, bit of trivia, that connects to where people have measured how finely you can discern frequencies here. And I guess we beat a lot of animals. And the theory is because humans need to have speech, and speech requires a lot better frequency resolution. So I tend to agree with that. But anyways, the problem is it's ill-posed. If I give you a number and I say 3 numbers added up to get to this one, what were they? You'd be like, I don't know. 5 plus 5 is 10, but so is 4 plus 6. So how do you separate it? You must have models where you make a hypothesis, right? At least in computer vision, the thinking, at least when I was studying it more regularly, is that your brain poses a hypothesis. It sees, does this explain what I see that's sort of been flattened into a 2D image? If it works, especially over time, then that's the correct assumption. And I haven't studied the audio system as much, but I'm guessing probably something similar happens there. There's probably a hypothesis thing that's going on in hypothesis checking. Okay. Loudness perception. I'll cover that, and then I'll talk about masking with some demos. Okay, have any of you seen curves like this? Okay, cool. So these are sensitivity curves or equal loudness curves. The threshold here is how loud, okay, so the frequency axis is along the bottom. How loud does a sound have to be for you to say, there's a sound, I'm no longer sitting in a room full of silence. I hear that sound. And so the lower a curve is, if you look at this red curve down here, it means that at that frequency, you only need a tiny sound and you can say, I hear it. So that means you're sensitive. And then if it takes a loud sound, like here, 70 dB at 20, it's got to be pretty darn loud for you to even know it's there. Okay, so that's what these curves represent. But so instead of plotting the sounds you can just barely hear, if you say, all right, well, let's crank up the sound that you could barely hear down here, let's just make it this loud. Let's make it 20 decibels. And then you say, all right, let's change the frequency. Let's give you one here. How loud does that have to get for you to say it's the same loudness as some reference, right? And then you can plot this out. So all these volumes, as you move in frequency, to the human ear should have the same loudness, right? So as you get to loud values, the difference between frequencies is not as great. Okay, and then you do A weighting where you can say, all right, here, I've got a soundtrack in a movie, this explosion and people are talking, you hear metal things falling, is that too loud? Well, you don't really know unless you know the frequency content. You push it through weighting, and then if this is the weighting curve, this ISO curve here, it's the inverse, or in the log domain, it's just like negative, right? Instead of 1 over. You flip that, and you can say, I can take my sound, it's got whatever spectrum, I'm going to multiply it at each frequency point by this red curve, and then it'll give me a numerical value when I integrate, and that will be my loudness. And I can compare that to, does the FCC allow this level of loudness? Or according to some standard, like in a theater, is it too quiet? Can people not hear the explosion and get that same effect? Okay. All right. So as you can see, there's nonlinearities, and so you can exploit this when you do a audio codec, right? You can say, well, you couldn't really hear this, let's not send it, or let's use fewer bits, and we can just quantize living daylights out of those components. Oops. Okay, so let me get into some demos. MP3, as everybody knows, it made file sharing through Napster really easy because it was smaller. But how did it do it? It used a bunch of different tricks. It used DCT. You get some energy compaction. It uses FFT as well, which AAC punted because they found that the modified DCT was better to just go with that for coding efficiency. But MP3 used tone masking, spectral masking, among other techniques. So I'll give you a tone masking demo. That's where if you have one frequency, like one tone, and I'm just using pure sine wave, a pure sine wave, and I'm playing it at a certain volume, and if I play another pitch that's a little bit different from it, I'm using like 440 and 450 hertz. So you got concert A 440, and then 10 hertz above that, dropping it down. We can vary the threshold. I mean, I tested on my laptop speakers. We can test with these. And then you'll see, can you hear that 450? So. Okay, here goes. All right, so that's piercing. All right, so if I mute this, do you hear a difference? This is just the 440. You might hear a little bit of beating between the two because they're close. And just to prove it's there, this is the 450. Okay, it is quiet. If you make it louder, you'll get this beating effect. Oops, sorry. Mute. I think I just crud. Did I accidentally delete it? Okay. Okay, so they're roughly the same volume, and you'll hear a beating. Oops, sorry. That's my bad. Sorry, it's just hard to do lefty with the mic in my hand. Here, I'll just force it here. 4 seconds. So you'll typically hear that. I heard that that's due to nonlinear response in your ear that caused the beating, but got to look more into that. So anyways, you could hear the effect of that tone masking, I would think. Like when the big tone was there, the small one was, if you could hear it, probably you couldn't hear it as well as if when it was by itself. Okay. And there's another thing called temporal masking. And that's where your signals occur in at different times. And this water droplet will be kind of quiet. I'll play it. Uh-oh. It's pretty quiet. Let me see. I'll turn up the volume a bit. Okay. Can anybody hear that? It was really soft. Okay. Okay, so if you slam a door and then you have a little water droplet or you drop a pin, as long as these two events are close in time, the loud one wins, and you're not supposed to hear the other one. That's different from if you drop a pin while the door is being closed, right? They're simultaneous. Then you're looking more at like the frequency masking effect. Okay, so I'll just enable these two. So this is a door slamming. It had echo. I wanted to cut it off so that the echo wouldn't step on the water drop. I really wanted to keep these two distinct. All right, so. All right. Whereas if you don't have the door, right, I mean, that's kind of pretty big difference in volume. So, you know, if we make this full volume, then you kind of catch the last end of the droplet, right? So anyways, if your encoder can find things like this, your lossy encoder, then it can say, hey, I see this little tiny blip that occurs after this loud sound. Let's just not encode it. You save the bits on that. So, all right, that's a pretty simple demo there. Okay. Okay. Any comments or questions? Okay. Okay, so let me see. All right, so this is the last slide for the first part of the talk, which is just a summary. So audio, actually no, it's not a summary, sorry. It's sort of a list of just a few of the formats that you've probably seen, right? So uncompressed is just like sort of raw sensor data, if you will. Or it's a nice format, like a mezzanine format that you can work with, and you don't have to worry about multi-generation quality loss. So PCM Wave's pretty popular. B-Wave, which is for broadcast, but that's also, because of its extensibility, it's been modified to also hold Dolby Atmos files as a single file. And so like your bed, your object data, metadata on position, all that stuff is all bundled into a single file, which is nice, right? Handling file sets, it's sometimes you can lose a file or mix in the wrong one. There's other ones, but those are the main ones I've seen. Okay, so lossless compression, you've probably heard of FLAC. Apple lossless, which I think they put inside an MP4 container. Monkey's audio, or .ape is the extension. I think that one does a little bit better than FLAC most of the time, but it's computationally more expensive. including on decode, although I know there's a mode you can compress, make the encoder work harder so that the decoder works less hard. Yeah, WavePack, MPEG, the scalable ones, they have like a base layer that's lossy, and then you can decide, do you want to add in enough data to make it truly lossless. Even the DLC is a compression format that's lossless for IAB audio, immersive audio, that's used in DCPs that you'll see in like theaters. When you go to theater and it's immersive sound, it's IAB inside it if it's got object-oriented data. So it uses linear prediction, and then it just codes the residual. Okay, and then lossy compression, you're probably familiar. We were talking about MP3, a little bit on AAC. There's Opus, Dolby Digital Plus, and then DTS has a perceptually lossless version under their master audio, their DTS MA. But DTS, the old, what they call digital surround and high res are lossy. You can set, fixed bit rate. Microsoft WMA, you got the open source Vorbis, even the old Sun AU, that's also lossy. Okay, I was going to talk about like how to mux these into different containers, but I realized that would just be like a huge topic to cover, and so this concludes the sort of audio perception part of the talk, and then I was going to talk about muxing. Okay, so you can mux you can mux different essences together: captions, audio, image track, user metadata, right, into a single file. And there's some example formats or container file types. Or you could mux different tracks into like sort of a multi-file package, right? DCP, they used to be shipped with hard drives to theaters. I don't know if they're still doing that. But there's multiple files kind of bundled together. You've got metadata files that have no kind of pixels or anything that's shown to a user, but they tie everything together. Same thing for IMF. Atmos has a sort of mezzanine non-single file format where the audio samples are in the one of the files. So I'm going to focus on IMF. Just because, I don't know, I figured maybe someone here has or will need to publish files to Netflix. Has anyone used like Photon to validate an IMF before submitting it, or IMP? Okay. They open sourced this project called Photon, or a tool, I should say, where it can validate your IMF. And one of the things that it checks for is audio and image tracks have to be exactly the same length, not even a fraction of an audio sample. And so initially we thought, oh, that's not a big deal when I was at a previous company, but it turns out that there's a few things that can happen, especially in combination, that make it a little tricky. Okay. So, the interoperable master format defines, it has a whole bunch of requirements. So, if something's going to be IMF compliant, it has to satisfy a whole bunch of different requirements. They specify image track has to be JPEG 2000 or high throughput JPEG 2000, which they added later. Audio should be 48 kilohertz, 24 bits per channel, and so on. But I'm going to focus on this exact track duration. Okay, and so in the spec they say if you've got 48 kilohertz audio and you want to match the duration of the audio to a I'm going to use the word image track because that's consistent with the standard, right? Because if you say a video track, what does that mean? Because video sometimes means everything together, including captions and audio. All right, so an image track where the pictures are at 2997 or 49, which is actually 30 divided by 1.001, like to be exact, or 60 divided by 1.001. And the standard says that must be a multiple of 5. And why is that? So we can just look at the math. The audio samples at 48 kilohertz for a single 2997 frame time, right, the length of time you would show it on a monitor before you flip to the next frame, is 1,601.6 audio samples. And so you could end up with 0.6 as your error, right, or 0.2, 0.8, or 0.4. But if the number of frames is multiple of 5, the number of audio samples is an integer, and there you get your exact match. So that's where the 5 multiple comes from. And the math is similar if you move to 60 frames a second, right? So 60 divided by 1.001, it's just half that. So the audio samples per frame is 800.8. So you got to go all the way up to 5, so that 5 times 0.8, that gets you your integer. And so the same thing happens there. Interestingly enough, if you were to have like a 24 divided by 1.001, I don't know of that frame rate as a standard frame rate, but I've seen at least like in Apple, you can specify 29.98, and I don't think that's 24 divided by 1.01. I think it's literally 29.98, and then infinite zeros after that. And there's no time code spec drop frame for 24 divided by 1.001. There's no SMPTE spec for that, so I think that's kind of a rogue one. But at 24 frames a second, 30, 60, and I think even 24 divided by 1.01, I'll have to check the math on the last case, you don't have to worry about this 0.2 kind of getting in your way. So you can just have any number of video frames. Like one video frame equals, an integer number of samples for the other frame rates. But these are common enough that you can't ignore them, right? They're not just some esoteric thing. Okay, now something that can complicate your things, your processing is if somebody submits a video, it's got an image track, and let's say the image track is at, 24 frames a second, and they want to convert it to another frame rate, and it's not an integer, it's not nice. Or let's say it's 29 and 7, and they want 60 out. And then you've got audio that maybe it was lined up with the original one. When you do the frame rate conversion, you got to get lucky to end up with exactly the same length for your display time for all your new frames. Okay. We're going to make 2 assumptions in the following slides: that you can't extrapolate motion if you're using like a high quality motion compensated frame rate conversion tool, and that it's bad to trim to fit because you could be destroying artistic intent. Say you've got a commercial and it ends on a punchline in the last 1/5 of a second. Some door slams and that's funny and you end it right there. That's sound, right? And you might have a flash that gives you a clue. Maybe it's the end of a movie and a hand comes out of the grave and you're like, oh, a sequel's coming up, right? So you don't want to destroy stuff by clipping too much or at all. So it depends on whether your customer cares. Okay, so we're going to assume that you cannot destroy data by clipping it, by shortening the end, by throwing away samples, and you don't want to extrapolate motion to get a new frame. So I drew this star here. So your input frames here, you're going from a high frame rate to a low frame rate, right? Your low frame rate has bigger frames time-wise, times the axis. Sorry, I didn't label it. So your input frames are shorter in duration because it's a high frame rate. Your output frames are displayed for a longer time. And let's say by the time this frame ends, this is actually, 0.1% over frame time because the 1.001 is not exactly 1.00. So let's say that occurs right here, and you're like, hey, I still have data. When this thing ended, this frame hadn't started. It started very soon after. Okay, let's just take that and make a frame. We'll have to hold it longer because we're on a slower frame rate on the output. So you're getting this lengthening right here because you can't just show this final frame for the original frame time, right? So if your audio matched up to the end of the original, what do? Right? It's typically standard just to add silence. You might want to ramp down. Usually audio, even on input, typically won't end on a non-zero value, but in case it does, you could ramp down. At one of the companies I worked at, you can do an exponential ramp down in about 4 or 5 audio samples, and you won't hear a pop. So I was surprised that it could be that short, but it worked at least on the hardware we were on. Okay, you could you could also shorten. If you go from a fast frame rate to a slow frame rate, you can get either. So here's the last time of action. What I'm assuming here is that the beginning of this frame is when the new motion occurred, not like somewhere in the middle. So let's say this frame ended just beyond this line here. Then that means when this one's done displaying, you've got nothing, right? Because this has occurred before. So if if you refuse to extrapolate, if you kind of want to be a purist, then you just have to stop. You say, I have no new data to synthesize this new frame, and so your duration then has to go from the original that's here, and it'll shrink down to here. So you can lose or gain time, and no matter what your original audio was, you're going to have to do something about it. In this case, you could just pad your audio to silence to meet this new longer image track, but here, your audio is sitting here. So you got to decide, what do you do with this frame here? Do you just repeat this last one and then pad silence to your audio, which ended here, out to meet the new extra frame? That's what I would recommend. Okay, and then going the other way, if you go from a low frame rate to a high frame rate, these are long frame times because it's slow, like 24th of a second. And if your output frames are, let's say, 5997, then, and this could be in the context of IMF or not, so your original audio went all the way to here. This small frame, let's say it ends and it is just beyond this start of action, then you can get nearly an entire slow frame that's lost, right, of shortening. Or the other way, if you finished here, you can like, hey, I can make one more, and then you're still short, right? So when you go from a low frame rate to a high frame rate, you only lose, the question is how much, okay? So then, what do you do with the audio? If it's out to here and the audio has meaningful data in this final frame, then you've got to decide what do you pad for the video frames. If this happens to be an IMF thing, you can get this like cascaded effect that you can finally resolve, where if you're short here on the video, let's say right here you're on a multiple of 5 and it's one of those weird frame rates, 30 over 1.01 or 60 over that. Then what if this was your multiple of 5 but your audio's out to here? So you add a few frames and you're like, crud, I just ruined it. I'm not at a multiple of 5. Then to do it correctly for IMF, you've got to pad to the next multiple of 5 and then potentially add silence to your audio to match. So if you want to be a purist, you probably want to tell your customer, like, hey, we could stretch your video by up to, whatever, right? 5 frames, 4 frames. And if their audio was initially longer, like even longer, like there's a mismatch on input, say their audio ends past this line, then you're going to have to add frames no matter what, and you could end up needing to add chunks of 5 frames to finally catch up with the audio. Let's say you get audio that's 1 second longer, you could add 20, 25 frames, maybe more, depending on whether you needed to add stuff here. Right, it's arbitrary how much of a mismatch you have. Sorry, so that kind of covers this. So, what do you tell users? Do you just silently fix it for them? Do you warn them? Do you block the job? I don't know if any of you have encountered this issue, but you got to have some sort of action decided, right? So it's just good to know. Or if your software automatically fixes things, but you end up adding 20 frames because our audio was really long and you had to get to the next multiple of 5 frames, then maybe you want to tell them, or at least have an explanation ready when they can't figure out why they suddenly got an extra n frames. Okay. So I think we covered this. Oh yeah, so there was this discussion, this debate at a company I was at. Do you pad with black frames? Do you pad with the final frame? And I argued you should use the final frame. It'll look like your movie just froze there. And one case that could be bad is if the producer decides, let's fade to white. And then you insert a black frame, and what if this output video is just a reel that will be stitched into another reel? Say it's part of a DCP where you're going to play this and then you're going to seamlessly switch to another. You've got this fade to white, and instead of fading back from white in, say, the next reel, you've got this black frame that shows up, or multiple black frames, right? So the question is, how much does your customer care about artistic intent? or are they just going to QC this and fix it if they don't like it? So, it's whatever your application area is, or whatever, or if you're the customer working with your own software. Okay. So I think that wraps it up. Okay, so just to summarize, you can compress because there's biases in statistics, both from nature and like human language is another source, like human-centric sources that are not uniformly distributed. And the human perceptual systems that for biological survival have necessitated uneven sensitivities, and we can exploit that in lossless and lossy compression. Human auditory system, just to go a little bit deeper into the perceptual part, we have different sensitivities for different signal attributes like frequency and loudness, total harmonic distortion, things like that. The dynamic range is limited. Typical sensors in the human body are on a log scale to achieve a broader range. People have uneven ability to discern depending on what two signals, what aspects they have, including masking effects or lack of discernment there. And that feeds into lossy audio codec design. And then we covered muxing in the context of IMF, the multiple of 5 for certain frame rates, how to handle source duration mismatch or how it can cascade onto with these other issues, and then issues caused by frame rate conversion. So, okay, and that's all I have. Yeah.
Check, check. Okay.
Yeah.
So you were talking about inserting the black frame in the image. So my question is, why not just always default to doing your padding or removal on the audio track? Because I don't have any sources to quote this, but I'm assuming, at least from my experience, that my perception is that I pay much more attention to the image than I do the audio. And we're talking about audio with video here. Like if I was closing my eyes, obviously I'm paying attention to audio, so why not just always pad with silence or something like that and, cut the image where the image should always be cut?
I think that depends on the customer. If the customer is okay with whatever you're proposing or propose to them, then it's fine. I guess I was making the assumption that it's illegal to delete any samples of audio or video, and that you could have input that where audio is a lot shorter or a lot bigger. So kind of, yeah.
So they're delivering something to you that is skewed.
Yeah, it's probably just like a bad edit, or they just dropped in a file and said, good enough, ship it, get it processed. Yeah.
One more question in the back here, or as many as we need.
One thing I've wondered about is we had MP3 and then AAC, and then lossy codec development kind of seems to have died. I was wondering if you had thoughts on why that's the case.
It could be saturation in terms of what humans can come up with for coding, right? Like if you're talking about like lossy quality, there's a thing known as transparency, right? It's like how many bits of a particular codec do you need before the typical user or even golden ears cannot distinguish between the original and the encoded output when it's re-rendered in a it could be A, B, forced choice or whatever, where it's basically a coin flip is their success rate. They're just guessing. So it could be that we've gotten good enough that people are like, all right, we've got plenty of bandwidth, there's no incentive, or maybe we've kind of hit some sort of plateau, and it would take someone with a new innovative idea, maybe more studying of the auditory system to, I don't know, decouple, do source separation and properly encode each one or whatever. But it could be that the human ear model isn't good enough, at least not in all circumstances. That's just my guess. Are there what?
Age-based codecs? Sorry, that's a joke.
There could. It would use your laptop cam to look at how old you are, and then it would just tell the server, don't send those bits.
That's actually a brilliant idea. I'm going to patent that one.
You could do the same for vision, right? I'll just give them SD. You know,
Well,
they're-
that's kind
they
of where
don't
my
see very well.
question, my next question was going to be, is my vision's progressively getting worse as we get older. Mine particularly, I don't consider myself a video or audio file. Like I have a music background. My brother, I don't want to call him golden ears, but he's much more upset about compression in music than I was. I was making a joke earlier, but you know, obviously music is one area where I do hear it a lot. I see it in video, especially fast motion, especially soccer or football, like certain sports, but it doesn't bother me as much as audio does, especially high sound, you know, high frequencies, maybe cymbals and things getting compressed down to nothing. As a drummer, I hear it the most through drums and compression versus guitar and other instruments. Do you think that as people grow older and my vision maybe is more impaired than perhaps my ears are, I'm skewing myself towards that and favoring like, oh, I think video compression is much better than audio compression or something like that? There's got to be some play in that human perception.
Yeah.
I'm not sure there's a question there, but I just wanted to make that statement. I think see what you thought.
Well, I could make some comments. Yeah, I think different people have different fall-offs, you know, in their vision and their hearing. I always hear audio companies say that audio is at least 50% of your experience of enjoying a movie. So, and then if you're a musician, I could see like two unique cases. First of all, audio is very important to you. And the second thing is, if you look at MP3 and say, yeah, it makes things sound bad. Well, if you're paying attention to crash cymbals, they have very high frequencies, right? Very high. The timbre, there's a lot of harmonics that resonate up, probably due to the physics of the metal, right? Metal can resonate quite nicely. Sound travels through metal at something like 20,000 feet per second compared to air, which is like 320 feet per second. And so, if you look at MP3, I was really disappointed when I turned down the bit rate. I thought it would just quantize more. It turns out it has a low pass filter. And so that could be, you're maybe hearing those overtones getting, what do they call it, secondary frequencies, resonant frequencies? Those are probably getting stripped away, and you're like, this sounds like crap. You know, these don't sound like cymbals, you know, or at least not good ones.
That's exactly where it comes from when low bit rate MP3 stuff back in early, 10, 15 years ago. We can get if I produce something at 256 CD quality, it's good enough for my ears. Again, my brother would be like, no, it has to be wave. Everything's catalog is wave. No.
Well,
so anyway.
Yeah, that raises a good point. I talked to we had golden ears at a wireless audio company that I was at. His name was Matt Meyerberg, and he was our golden ears who would make sure our audio error concealment in wireless audio was working. So someone turns on a microwave or a cell phone, and not cell phone, a Wi-Fi or a cordless phone, which is horrible, has plus 20 dB, and it is in the 2.4 gigahertz wireless sort of unlicensed band. And we would drop packets, and we would have to fill them in. And he'd be like, okay, that's not filled in. Try the other algorithm. All right. So, but anyways, I asked him, like, how many bits do you need so that even golden ears are fooled? You know, what's their transparency level? This is way back when, kind of dating myself, but this was in like 2006-ish. Yeah. Back then, I guess Dolby's AC3 was the state of the art, and EC3 hadn't come out yet. And he said there about 550 to 600 kilobits, even most challenging material, probably no one on the planet could tell the difference in an objective A/B test. But it's probably gotten better since then.
Yeah,
but
so like
320 MP3 256. I've heard, you know, I don't have golden ears, but I remember some difficult musical passages, classical, can show that 256 is not adequate.
I have no problem at 256. Is that why maybe 768 EC3 Dolby Atmos is just so crystal clear and beautiful? It's because we're kind of above that.
Yeah, I think you're above that cutoff line, and
Yeah,
EC3 is supposed to be even more efficient.
Yeah.
So yeah.
Oh, that's awesome. I will say my brother works at Roland, a music company, for 25 years,
so
and so
awesome.
he's allowed to have golden ears, but no swag on him.
Nice.
All right, anyone else have questions? In the back.
We're seeing a lot of like spatial audio, spatial video type applications pop up, Apple Vision Pro, etc.
Mm-hmm.
How much of the existing tooling works for like encoding spatial information, and how much does the human audio perception system care? Like, I know ASMR on YouTube is a big thing with headphones and people seem to love it. So is that like a big deal that we're missing? And do we have tools to cater to that?
There's definitely the tools. I don't use them, but people in my group do, because they've worked with, they've done audio post-production for some of the biggest hits out there, right? Like, it's cool. I get to use like Black Panther 2 and Avatar as just my sample test files in my development, which is just, it just blows me away. Like, I hear, you know, Wanda the Scarlet Witch, I hear her voice in the Wanda test material. So they definitely work with immersive audio, and there's like a tool that shows like a 3D chart like this, and then as you play the audio, you'll hear the audio, but you'll see they have like this little movie theater diagram box, and you'll see a dot moving around. Like, that's where that sound source is going. If you don't like it, you can go in there and you can tweak the path. And so the tools all exist. I think the push in getting things out to market in terms of like, here, put on your stereo headphones and you'll still hear stuff going around. And I've heard demos, which is really cool. Like, you put on headphones and you hear a helicopter flying around you, or you hear birds that fly like above you and then in front of you and then to the side. And so I think that's what they're doing with like Apple Music when they have immersive audio. They're probably using the ear, the outside, you know, the analog signal processing I mentioned, probably, I'm guessing, to simulate that. So I don't know if it's like they're just trying to push people, because, you know, companies can make money. Everyone's was trying to push. You hear about 8K video, but unless you're sitting really close to the screen, it doesn't matter, right? Like 4K audio, you already have to sit. I think I showed the calculation in, well, it's talk number 2 of this meetup, 0.75 times the screen height in order to distinguish between pixels on a bright image. So I don't know. I guess immersive audio, we haven't gotten to the point where you only see like a 0.5% difference. It does make a big difference, right, to have sort of things above you as well, so you're in the hemisphere when you live in a planar world. So yeah, I'm not sure how to answer your question on like how much are we missing out if we don't have it. It's probably more a subjective thing. Yeah, I think it's kind of like, you know, where do most people land when it comes to audio quality? Like, why is the big screen no longer making much money, right? Theaters either lose money or just barely break even, because convenience is king. You can watch a short thing on Netflix. When you exit, it just keeps your spot in the movie and come back to it. You can watch it for 3 minutes in a bank line while you're waiting for the teller. And is the immersive audio going to be big? I think it'll continue to grow, because you get immersive audio if you can do it through stereo headphones. It's like, why not? You don't lose the convenience in order to pick up the quality. Not like you have to go to a theater to get the quality. People are like, it's not worth it. But if you can just throw on headphones, maybe that will continue to grow.
You started to touch on it right there. My next question is, or maybe just asking for comment or what you see in trends, but like, is there a push for changing mastering or providing secondary mastering for home, mobile, stuff like that? You know, there's these movies, you know, on Disney Plus or whatever. They're huge dynamic ranges, and it's like, I'm watching this at 11 p.m. and my kid's in the bedroom next door, and I have to put on subtitles and turn the volume down, right? And it's like, I need a mode where I just need to like, I need that compression. And yeah, okay, it's not the most immersive and whatever experience, but like, it's better to be able to at least hear the audio of the dialogue, right? Like, this is you know, it's like, I would say it's even in popular culture now. People are talking about the rise of subtitle usage and stuff like that. Like, I personally use subtitles because kind of part of that reason, but other reasons too. But yeah, it's just interesting.
Yeah, I think I think Dave Griggs, who spoke here 2 times ago, I think he said that the home market is where he wants to see more of the technology placed to make mixes that sound good in a, well, not in the kids asleep mode, but just in a normal listening mode. But in terms of like quiet mode where you lift the dialogue and decrease like the booms of the explosions, I think all the tools exist that could do that. I think it's up to the content providers. Do they want to provide that switch? Either dynamically send you what you want, or just have it all together, burn the extra bandwidth, and you pick it on the client side. I don't know, what people would decide there, but
discussions like happening about
Well, I've seen related discussions where people want to meet dialogue accessibility requirements. Some people, they either can't hear it because they're not sensitive in that 1K to 3K or 1K to 4K frequency range in their hearing, or they can hear fine, but if there's background noise, they just don't have the audio processing to do that, hypothesis separation, and they can't hear the listening. So I think you could take that same technology and use it for the kids asleep mode. MPEG-H will do it. Fraunhofer gave us a really nice demo where if you have the dialogue source, I believe you can change the thing. I think Brazil accepted it as their standard in their broadcasts, and it has some nice features. So that the technology exists, I think it's a matter of the people rolling it out. The streamers who give you the app to download, are they going to allow that and have their servers serve it that way? I mean, I think it's there. It's just a matter of someone deciding to do it.
So, yeah, AV amps, and it'll on purpose it will crush it. Instead of doing the dynamic range, it will reduce the dynamic range so you can. Yeah, so it will just bring the loud down and the low up, so you could have it at a low volume and hear everything, rather than having to really turn it up and then suddenly an explosion.
Okay.
What about when I'm eating chips? Just kidding. I do hate that though. I get like some chips and I'm like, can you turn it up now? And then it's too loud. She's not eating. Okay. Anyways, any other questions? We are pretty much at the top of the hour, so we can certainly talk after this. We have some social time. I think we have till 9:30, right? Yeah. So let's put our hands together for Al. That was an amazing talk. It really was.